Resonance structures are a more complex version of a Lewis structure that needs to be drawn to represent what sometimes happens with molecules when they have multiple bonds and they have potentially a formal charge. If you've been following along on all the lessons about Lewis structures, you already have this written down. If you don't, pause it right here and write this down, because these are the steps that we're going to use to successfully draw Lewis structures. Not just Lewis structures that have resonance structures or resonance hybrids, but any Lewis structure. If you follow these steps, you're going to get it right every single time. And one of the things that you might notice if you've been working along with me here is that we have not needed to do this yet. We haven't needed to do step 5. But we're at the point where we're going to learn step 5, and now anytime we run into a resonance structure, we're going to be able to draw it. What is a resonance structure? Well, here's the thing. This is kind of weird and it's kind of complex, but let me walk you through it. When we show a resonance structure, it's just the dot structure diagram or the Lewis structure diagram that shows all the possible configurations of where a double or triple bond is in a molecule. I've drawn, or roughly drawn, a Lewis structure. This is just the skeleton structure, where the double bond is in this position, and the double bond is in this position, and this one, and it's over here. Now, a student had a really good question at one point and said, well, isn't that just rotated? Like, why does that matter because it's just rotated? Well, yes and no. Because in a Lewis structure, we're drawing it on a piece of paper, right? We're taking it in 2 dimensions on a flat plane. But molecules live in the 3-dimensional world. So we're giving an artistic representation of it. But what we need to understand is that this thing actually lives in 3 dimensions. And because it's 3-dimensional, we have to be very careful about how we draw it in 2 dimensions. My disclaimer is this: there are several ways to draw resonance structures. But I'm going to stick with the method that I'm going to teach you now, and it will work in all situations, but just know that down the road, you might find another method that's going to be easier in the situation that you're doing it. And when you're drawing Lewis structures, here's a great question that I get from students. How am I going to know if I need to draw a resonance structure? Well, here's my answer. You won't until you draw it. And if you follow these steps that I just had on the screen, then you're going to know when to draw a resonance structure, and you're going to get it right every single time. The best way to learn is to do examples together. Let's start with sulfur dioxide. I'm going to go through all of my steps. The first one is to add up how many valence electrons I need in my structure. This is sulfur. I have 1 sulfur. Oxygen, 2 oxygen. You can see them right here. I find sulfur over here on the periodic table. It's in group 1, 2, 3, 4, 5, 6. 6A, which means it has 6 valence electrons. There's only 1 sulfur that's going to show up to our party. So I'm taking 6 times 1 is 6 valence electrons. Oxygen, well, look, it's in the same group. So it also has 6 valence electrons. But we have 2 oxygens that are going to show up to our party. 6 times 2 is 12. And then I just add these up. 6 plus 12 is 18 electrons. I look for a formal charge. That would be a positive or a negative or a -2 or something up here. It does not have one of those, so I'm done with step 1. Step 2, build my skeleton structure. Well, which one of these is going to go in the middle? The one with the lowest electronegativity will go in the middle. And electronegativity trends this way. So as you go that direction on the periodic table, electronegativity goes up. So this is going to have sulfur, is going to have a slightly lower electronegativity. We'll put it in the center. I don't know where these oxygens go yet, so I'll just go ahead and plop them like right here. I need to add my 18 electrons around here. So far I've used 2, 4. I'm going to fill up the outside edge. 5, 6, 7, 8, 9, 10. Let's go over here. 11, 12, 13, 14, 15, 16. I need to have 18, so let's go ahead and put 2 on here. Now I've used up 18, and I really hope that, sorry, I forgot to check these off. I hope somebody out there in the world is saying, wait a minute, there's a problem. This sulfur is not happy because it needs to have 8 electrons around it. That's the octet rule. This oxygen has 8, this oxygen has 8, but sulfur does not. We learned a rule in multiple bonding that says if we have an unhappy central atom and we've run out of electrons, what do? Well, I like to say that sharing is caring. So I'm going to tell this oxygen to share 2 of its electrons over here. Don't write this yet. So I said that that oxygen needed to share its 2 electrons over there, but why does it have to be that one? That oxygen's going, why do I have to share? Why can't that oxygen share? And this oxygen over here is saying, haha, you had to, and this one's saying, but why do I have to share? I'm no different than that one over there. Maybe it should share. And what you're going to start to see is that this is what actually happens. The double bond is here right now, but that double bond will resonate and end up over here. And then will resonate and go over there because electrons don't care about our rules. Electrons are moving. We're drawing them stationary. We're drawing them in a specific position. But in the real world, they are moving all around the outside of the electron and really, the atom, and really around the outside of the whole molecule. So this double bond won't stay there. It'll end up over here, and then it'll be over here. And so if any of you are like music people, and you know that if you hit 2 cymbals together or you strum a guitar, it continues to make noise for a while because it's vibrating. We call that resonance. That's what our sulfur dioxide double bond is doing. It's resonating back and forth. Let's go back. Does it have a formal charge? No. So now I do need to include resonance structures with brackets. Brackets means I'm going to go ahead and put brackets around my SO2 like this. And then I need to draw resonance structures. Resonance structures are all the possible configurations of what we see. So it is possible, right? That's what we just concluded, that I have sulfur with a double bond over there and a single bond over here. And then we have the oxygen. I have to draw all the possible configurations. This is the other possible configuration for SO2. It's showing the resonance that the double bond is flip-flopping back and forth. We then put a double arrow between these. The reason we put a double arrow, I've kind of run myself out of space, is to show that I'm not drawing 2 separate things. This isn't 2 different sulfur dioxides. This is the same sulfur dioxide that the double bond is resonating back and forth to either side of that sulfur. That's it. This next one is a great example because it has all the elements for all the rules that I like to use for drawing Lewis structures. I would encourage you to pause the video, try this one on your own, and then come and check your answer. I'm going to work through this with you. If you want that help, let's break this up and figure out how many valence electrons we have to build our structure. 1 nitrogen and 3 oxygen. Each nitrogen over here is in group 1, 2, 3, 4, 5. So 5 valence electrons times 1. Oxygen right here, the group next to it. That means it has 6 valence electrons. I should show you probably 1, 2, 3, 4, 5, 6 A. 3 oxygens. 6 times 3 is 18. Then I just add these together. 5 plus 18 is 23. Add or subtract electrons to reach the formal charge. Don't forget this part. Let's look. This is the formal charge. We have a negative charge. If we have a negative charge on our compound, it means that a negatively charged electron had to show up to the party to get this to form, to get it to work. So I need to show that another electron had to show up for this structure to work, or for this molecule to actually hold together. That means I have 24 electrons to build it, not 23. For our skeleton structure, what's going to go in the middle? We have oxygen, we have nitrogen. Oxygen has higher electronegativity. I can see that because it's farther, closer to this corner. Plus, there's only 1 nitrogen. That's a pretty good indicator that that's going to be our central atom. So I'm going to put my nitrogen here. Not totally sure where the oxygens go. I mean, I am, but if you're not totally sure, that's fine. Just put them somewhere and follow the rules and you'll be good to go. So let's put our 3 oxygens on here. Notice I'm drawing this smaller because I know I'm going to have some resonance structures that I need to draw with it. There we go. We built that. Add electrons around the outside of the molecule till I've used 24. Right now I've used 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Oh, 24. I'm all done. I don't have any more to put on there. Well, what do I do then, right? Because I've used them all up, and I know this nitrogen's not okay because it only has 2, 4, 6 electrons. That's not going to work. Well, we just talked about if I have an unhappy central atom and I run out of electrons, I need to share. Well, which one is supposed to share? That's the point, right? This is the resonance. So if I say, okay, this oxygen needs to share 2 of its electrons, it could have been this oxygen or this oxygen. In fact, it is any of those. That double bond will transition or resonate from this position to this position to this position to this position. And all of those are possibilities of the configuration for the nitrate ion. So I'm going to pause here knowing that I need to draw more resonance structures, and I'm going to go ahead and fill out the other things I need to do for this one individual one. Add brackets in the charge if it has a formal charge. It does have a formal charge. So I'm going to go ahead and put brackets around it like this and put that negative up here to show that it has a formal charge. Now this nitrate ion is correct. It's fine, it's good, but it's not showing resonance, which means, and I'll just go ahead and put the brackets in first so I know how much space I have. I need to draw 2 more of these because think about it. That double bond could be here or here or here. Put a nitrogen there. I know I need 3 oxygens. I just need to change the position of where the double bond is. Doesn't matter where I put it. I'll put it right there this time. Put these this direction. And I need to be careful with my electrons because we can only have 8 electrons around each of these when we're done. So notice I just put a lone pair there and a lone pair there because it already has 4 electrons in the bonds. And I'll plop these on here. I need to remember to include the formal charge right there. And let's draw the other version, which is going to exist. We got our nitrogen in the middle. We know we have our 3 oxygens, and we need to show that double bond existing over here because I haven't shown that version yet. And plop on our electrons, make sure we have the correct number. Don't forget the formal charge. And here's our formal charge. And I'll just use a different color so we can see them. It's always good to put the double arrow lines here. What that's doing is that's reminding us that we understand this isn't 3 different nitrate ion compounds that we drew. It's the same one, and the double bond is resonating from all 3 of those positions. Stick with me. The next place we're going to go is expanded and incomplete octets. We've been following those rules that I gave you very, very closely, and we've been drawing great Lewis structures. But now we're going to find out, oh boy, sometimes those rules are broken. And when they are, it's called an expanded and an incomplete octet. And in the next lesson, I'm going to walk you through everything you need to know to be successful in drawing Lewis structures for incomplete and expanded octets. There's lots popping up on the screen. You can come learn things. You can come and see me blow things up and learn other chemistry and science experiments at bealscience.com. I just hope to remind you to keep on learning.